Whenever we wiggle a rope or see a wave in the sea, we can see a wave being emitted from one point to the other. But what about when we see planets, stars, and black holes moving around the universe? Are they oscillating? Are they emitting some types of waves as well? This question will lead us to unravel the mysteries of the oldest known force that shapes our cosmos and leads to mesmerizing ripples throughout space-time. Gravitational waves are distortions, or ripples, in the fabric of space-time caused by the movement of massive objects, such as colliding black holes or neutron stars. This groundbreaking concept emerged from Albert Einstein's theory of general relativity, published in 1915. Gravitational waves were first predicted by Albert Einstein in his groundbreaking general theory of relativity. But to truly understand them, we need to start with the foundation, Einstein's field equations. Don't worry, we won't get too lost in the math today. I'll break it down for you step by step. So, Einstein's field equations express the relationship between the curvature of space-time and the distribution of matter and energy within it. In simpler terms, they tell us how the presence of massive objects like stars and planets affects the geometry of the surrounding space. Let's take a closer look at each component. Here, G mu v represents the Einstein tensor, which encodes the curvature of space-time. T mu v represents the stress-energy tensor, describing the distribution of matter and energy. And G is Newton's gravitational constant, while c represents the speed of light. The Einstein tensor accounts for the curvature and how it varies across space-time. Think of it as describing the warping and bending caused by the presence of matter and energy. On the right side of the equation, we have the stress-energy tensor, T mu v, which represents the distribution of matter and energy throughout space-time. The stress-energy tensor encompasses everything from mass and energy density to momentum and pressure. It essentially tells us how matter and energy are distributed and moving in the region of space we're examining. Now, when we solve these equations, we're essentially finding the relationship between the curvature of space-time caused by mass and energy, and how that curvature influences the motion of objects in that space-time. Although this seems a rather simple and small equation, Einstein field equations represents a set of 10 entangled equations so hard to solve that even Einstein himself thought that no one could ever solve it for any particular case. However, under some approximations, we can get what is called the linearized theory of gravity, a much simpler set of equations which allows us to simplify calculations and gain insights into weak gravitational fields. This rather simple equation gives rise to a closed solution of what is now known as gravitational waves radiating through space, where h is mainly measuring the variation from a standard flat space-time. These waves are so tiny and carry such a small amount of energy that it was not believed that it could ever be detected. Even though the direct observation of gravitational waves took 100 years after its theoretical development, in 1974 we already had a great hunch that it should exist. Hulse and Taylor discovered a binary system, PSR 1913 plus 16, in which both stars are very small, and one of them is a pulsar. The period of the orbit is 8 hours, extremely small by astrophysics standards. The fact that one of the stars is a pulsar provides a very accurate clock, with respect to which the change in the period as the system loses energy can be measured. The result is consistent with the prediction of general relativity for energy loss through gravitational waves. This system is decreasing its period with the rate of 76.5 milliseconds per year and will eventually collide in 300 million years, where it will emanate its highest amount of gravitational waves. The data suggested that while Einstein's predictions were plausible, they were not conclusively proven. The initial experiments were not a direct measurement of gravitational waves themselves. Instead, they indirectly hinted at their possible existence. To firmly believe in gravitational waves, scientists needed to observe their effects on moving objects. However, achieving this was no simple task. It took nearly 4 decades of scientific advancements and technological breakthroughs to reach the point where scientists could directly detect gravitational waves. One of the critical developments was the construction of the longest laser ever built, which would become a key component of the groundbreaking experiment. The discovery of the gravitational waves is well cemented in the Nobel Prize awarded for Rainer Weiss, Barry C. Barish, and Kip Thorne, in the name of the LIGO and Virgo collaborations for the detection on September 14th of 2015. However, our story starts much earlier in time, when the first ideas to even attempt to detect these waves began. The first device created to detect was built by Joseph Weber in the late 60s, for what is now known as Weber's bars. He built a cylinder that slightly resembles an antenna that should resonate exactly at the frequency of the supposed gravitational waves. Not only that, he didn't only build the device, but on 68 he even detected the gravitational waves. At least, that's what he claimed, because it was never possible to replicate the result. More than a decade later, in 1984, Weiss has the idea to develop a device that could measure gravitational waves, but this time, instead, based on a Michelson-Morley interferometer. If we set 2 lasers pointed to 2 different hanging mirrors separated by a 90-degree angle, and both lasers are in phase, if something slightly changes the distance of one of the mirrors, in our case, a gravitational wave, the 2 lasers won't be in phase anymore. Despite the simple idea, in order to detect something that weak, we'd have to build lasers and tunnels 4 kilometers long. It was only in 1992 that the National Science Foundation in the United States recognized the potential of this project and provided funding for the construction of the LIGO Observatory, and the first run officially started only in 2002. The very idea of detecting gravitational waves was already very discouraging due to its weak interaction. But we must also point out what an engineering marvel such a device is. There had never been created a laser so stable that could reach a 4-kilometer distance with pinpoint precision. Creating and setting a mirror so light that could hang with the thinnest string to lower any friction effect, and sensitive enough to move with the slightest gravitational wave that passes on it, but hard enough not to fall over from the pressure caused by the laser. Creating a machine so sensitive that even an airplane flying near it or cars crossing close to it could change the data. And due to all those reasons, the LIGO Observatory failed to detect anything that might resemble a gravitational wave. In the following years, scientists continued to improve and upgrade the LIGO detectors to increase their sensitivity. The enhanced version, called Advanced LIGO, came online in 2015, with even greater sensitivity than the original detectors, and only then were we able to finally detect these almost invisible waves. As obvious as it may seem now, there was a huge uncertainty if these observatories would be able to detect gravitational waves. So one of the most important discoveries from the observatories was to verify the existence of gravitational waves. And not only that, but we also solved another huge problem hidden in the theory of general relativity. Black holes are indeed real. We have already detected the coalescence of 90 binary black holes, 2 binary neutron star black holes, and 2 binary neutron stars. With the ongoing run of the LIGO, Virgo, Kegra observatories, we will certainly reach more than 100 observations, ranging from 7.8 to 142 solar masses. Besides all that, we are also putting general relativity to the most excruciating tests possible. We found that the speed of gravitational waves, which is intrinsically tied with the speed of gravity, is really close to c, the speed of light. That is, the graviton, if it exists, should be massless, and the up-to-date values corroborates with all of that. We didn't only find gravitational waves in black holes, we started a new era of astrophysics. Just like Galileo created a telescope and aimed it upwards to see planets for the first time using electromagnetic waves, now we have a new window to the universe. The realm of gravitational wave astronomy has just begun. In this new era of astrophysics, where we have been gifted with revolutionary ways to unravel the secrets of the cosmos, one of the latest additions to the game is the Kagra Observatory, which has just joined forces with the renowned LIGO-Virgo collaboration. Located in Japan, this observatory will play a crucial role in our quest to understand gravitational waves. But that's not all. There's more to come on this cosmic adventure. Let's talk about the Indigo Observatory in India, scheduled to be completed by 2030. Once operational, it will significantly enhance our gravitational wave studies. Not only that, by the 2030s, we'll have the awe-inspiring Einstein telescope in action. The wonders don't end there. Brace yourselves for the future of space-based observatories. We have Tianqin, Desigo, and LISA, just to name a few. These incredible ventures will dominate the upcoming decades with groundbreaking research in gravitational wave astronomy. So, what does all of this mean for us? These experiments open up a universe of possibilities. Not only will we continue unraveling the mysteries surrounding black holes, but we will also gain a better understanding of supernovae, those awe-inspiring cosmic explosions. Moreover, these observatories will help us discover more neutron stars, allowing us to delve deeper into their secrets and understand their composition. There's more. Picture this. We'll be able to detect supermassive black holes, those colossal giants lurking at the centers of galaxies, shaping the very fabric of our cosmos. But the excitement doesn't stop there. These experiments might even unlock the mysteries of cosmic strings. Imagine unraveling the threads that weave the universe together. It's truly mind-boggling. And here's the most mind-blowing part. We might even capture the gravitational waves sent by the Big Bang itself. Just think about it. We'll be listening to the echoes of the universe's creation. So there you have it. The future of astrophysics is looking brighter than ever before. With these groundbreaking experiments and data on the horizon, we are poised to unravel the universe's most profound mysteries. And here's the next video that you must watch. I think you've never seen a video like this on dark matter.